Hello everyone, this is Finnerpind from Treble HQ in Reykjavik, Iceland. Welcome to today's webinar where we will unveil version 2.0 of the Treble software development kit. And I think I can safely say that we have a very exciting event ahead of us with some new groundbreaking technology being released to the world. The agenda is that I will first give a short overview presentation about the SDK, but then the main bulk of the event is that we are going to demonstrate the SDK being applied to a variety of different use cases and thereby sort of showing various features and functionality of the SDK. Me and my good colleagues Daniel and Georg. And we'll look at product virtual prototyping, machine learning model evaluation, synthetic audio data generation, parametric analysis, and automotive acoustics. Then we'll share a few words about the licensing of the product and do a Q&A with the three of us. So let's dive in. First and foremost, of course, all credit goes to the fantastic Treble team. This group of brilliant scientists and engineers and entrepreneurs have been working really hard for a really long time leading up to today's event. And they've sort of struck again with absolutely amazing innovations that we're sharing here today. Well done, Team Treble. And we at Treble, we're very proud to be serving more than 150 organizations across the globe, leading firms within audio technology, big tech giants, engineering consulting, and so on and so forth. We see a few logos here on the screen. There are also many other impressive logos, which I'm not allowed to show, but yeah, we're just happy to be working with all these fantastic partners, and we really emphasize working closely with the audio and acoustics community and iterating on the products with them and so on. The Treble platform is summarized here in this picture, and as you can see, there are sort of three main components. The centerpiece is our proprietary simulation engine, which sits in the cloud, and then we have built sort of two interfaces to this simulation engine. On the one hand, what we call the application, which is a GUI-based, browser-based software product. And on the other hand, the software development kit, which is of course what we'll mainly be talking about today. And as you can see here, I write that the software development kit was soft launched in late 2023. So access to the product has been limited up until now. We've sort of had a waiting list where people can sign up and so on. But as of today, the SDK is becoming available for anyone, and that's a major fact. I will also say that everything that you will see in today's demonstrations, all features and functionality and so on, are included in the SDK today, robust and production-ready features, unless specifically stated otherwise that it's some kind of coming soon features. There is like one or two like that in the presentation. Okay, before diving into the SDK, just 30 seconds on the application in case you're not familiar with that product. The Treble web application looks something like this. It's a fantastic simulation software for a variety of use cases. I've summarized perhaps the main ones here, which is architectural acoustics and sound system design. Acoustic materials, we have a lot of material manufacturers and vendors and so on who also use the application, and for soundscape design. And exactly 3 weeks ago, we had a major webinar event where we unveiled the biggest update we've ever released on the web application. And in case you're interested in the web application in general or in that update in particular, I encourage you to check out that webinar, where you can see the link to the webinar here below. So that was the web application. Now for the SDK. The SDK is the world's first acoustic simulation software development kit, a Python-based programmatic interface to our proprietary simulation engine. And being a programmatic interface combined with the scalability of the cloud and all the advanced features that the SDK includes, makes it a very powerful and unique solution which can address a variety of interesting challenges within audio technology and acoustics. Many of them have to do with either audio algorithm development, DSP development and so on, usually, or at least very often, machine learning based algorithms, and then all kinds of product virtual prototyping. This combination of advanced simulations and scalability also offers very unique capabilities when it comes to data generation. So being able to simulate thousands of scenarios and use that to train and evaluate and develop machine learning based algorithms is a key use case of the SDK. And as I write here, advanced acoustic simulations at scale made easy. That's the SDK in a nutshell. And it can unlock accelerated design cycles because you can automate all kinds of workflows and integrate it into your custom workflows or even with existing products as well. And the SDK is already adopted by several of the large tech giants and other large technology companies, and we're excited to scale it up even further after today's webinar. And this has been previously mentioned, but just to emphasize the point, it really offers unlimited scalability, the SDK, thanks to the cloud-based nature of it. You can go from running one simulation to running 10,000 simulations back to one, without any problems, and these kind of advanced simulations. We also really use kind of very powerful computing hardware to accelerate the simulations, so our solution is much faster than any other existing acoustic simulation tool on the market. And then by being in the cloud, there are nice added benefits such as being able to collaborate with colleagues and have your history backed up and so on. I also want to take this opportunity to emphasize that we at Treble take data security extremely seriously. We are compliant with the strictest cloud security standards such as SOC 2. We're audited on that regularly, so you can rest assured that your data is completely secured within Treble's system, same as banks and other kinds of institutions. Okay, the core engine, just a few words on that. It is a proprietary, and we hold several patents on this acoustic simulation and spatial audio engine. A key aspect is that it allows you to blend very accelerated wave-based or finite element simulations and state-of-the-art geometrical acoustic simulations. So for small to medium-sized spaces, you can easily run wave-based only for the full spectrum. For large spaces or where you want to maybe run 100,000 rooms or something like that, then maybe you would combine wave-based and geometrical acoustics modeling using wave-based for low to mid frequencies and geometrical acoustics for high frequencies. Geometrical acoustics are essentially a high frequency approximation. And that allows you to strike a very good balance between, let's say, cost and accuracy. The engine allows you thereby to simulate any kind of environment, any kind of shape, any kind of material, any kind of sources and receivers and so on that you have in that domain with very high precision and ease. And we have placed a huge emphasis on the geometry input side of things. You can import geometries, you can programmatically generate advanced geometries, and you can also leverage Treble's huge database of geometries in your work. And then there's just a whole range of both pre- and post-processing capabilities, visualization, spatial audio, oralization, and a variety of other things, which we will of course show here today. And this is all based on very advanced science and recent breakthroughs within applied math, HPC, and acoustics. And the core engine has been validated in a large range of benchmarks, which you can see on our website and under our documentation. It has been applied to machine learning cases where data from the simulation engine has been used to train machine learning models, and then we see an improved performance of those machine learning models. We have applied it to these what I call isolated acoustic phenomena cases, such as diffraction around an object or reflection of a complex surface or something like this, benchmarking against this good database of measurements called the Benchmark for Room Acoustic Simulations. And we've also applied it to several types of rooms and environments and shown a very good match between measurements and simulations. Okay, that was the intro overview presentation. I think we now just dive into the use cases and the demos. First use case we're going to dig into is product virtual prototyping. And by extension, we'll sort of show a lot of the fundamental functionality of the SDK and how to set up a single simulation and work with the results and post-process the results and so on. So let's imagine that you are a headset manufacturer and you want to optimize the headset you are designing or producing, either the hardware itself, the form factor, the positions of the microphones in the microphone array, things like that, and you want to be able to virtually prototype that in a variety of acoustic conditions. Or you're developing some kind of algorithm that's within the device, potentially a data-driven DSP algorithm, and you want to generate high-fidelity data to train or evaluate that algorithm. That's exactly what the SDK is made to do, and we'll show this right here and now. So in this kind of scenario, you would like to set up a virtual audio scene. And an audio scene can look something like this. So it's a simplified sketch where we have the receiver device in question with some microphones on it. Then we have some environment with some furniture and stuff around and things like that. We have some, let's say, call it target sources or speech sources and things like that you want the device to pick up. And you have some distractor sources like the coffee machine or whatever that you want to reduce. And we can set up the audio scenes very easily in the SDK, have them simulated with high precision, and render device-specific output for those scenarios. I'll show it here for kind of setting up one scenario, but it's also very easy to do it at scale to set up 10,000 scenarios. We'll look at that a bit later today. So I'm just going to walk through the code here. The first block is just about kind of, let's say, logging in to the SDK and creating a project, which we call here DRTF, Device Related Transfer Function Example. And there are a few ways to get the geometry in question. You can use the geometry database. You can programmatically generate rooms. We'll look at both of those in a bit. But also you can import room geometries. That's what we do here. We support a wide variety of 3D file formats, such as 3DM, SKP, DXF, OBJ, and so on. So pretty much all CAD tools can output in at least one of these formats. And it's simply this code here to import and add the model to the Treble SDK. I've already run that, so here I'm just going to display the model in question that I'm going to work with. It's a model of an apartment. We are going to set up an audio scene in this sort of kitchen living room space within the apartment. And you can see that the 3D model, the surfaces, the walls and so on have been grouped into layers, which will facilitate material assignment, which is indeed the next step. So the Treble SDK comes with a huge database of all kinds of acoustic materials that you can use in your simulations. These materials are grouped into different categories, and right now I'm just fetching different categories from the database and pulling them into these variables here. And then I create a little function which randomly maps a material from a given category to a layer in the 3D model. And I do that for all the layers here. And now this function is ready. And then the way I assign materials in this particular case, you can go about it in different ways, but what we do here is that we say, please kind of iteratively assign random materials according to this function to the different surfaces until the Sabine estimated reverb time is in this range of 0.3 to 0.4 seconds. And it takes a few iterations until it's hit some group of materials on the different layers. If I would run this again, then I would get different materials, of course. And the Sabine estimated reverb time is within this range. Okay, we have a room, we've assigned materials. Next step, sound sources. The SDK comes with a very big database of all kinds of sound sources that you can use in your simulations or in your audio scene generation, which we see here. And the first thing I'm going to do is I'm going to pick two sources from this database. On the one hand, a speech source, and on the other hand, a particular Genelec speaker, the 8020. And I'm going to plot the directivity of the speech source just for fun. At low frequencies, it's quite omnidirectional. At high frequencies, it's directional, as expected. All right, we can also import directivity into the SDK, either if you have directivity in the CLF, common loudspeaker format, or if you just have raw data, a directivity balloon. It could be in an Excel sheet or in a CSV file or whatever, where you basically have frequencies, points on the sphere, and then the complex frequency data or the balloon data here. And that's what we do here. We've kind of created a little helper function here to fetch the measured balloon, and then we basically have these arrays of data, and we add that to our source library. Okay, so now I've kind of chosen what sources I'm going to work with. Now I'm just going to put them into the audio scene. So I make a list of sources here. First, I put the speech source in a particular location and give it a particular orientation as well. I also add an omni source somewhere in the room. I add the Genelec 8020 somewhere. And finally, this custom source with the raw balloon data, I also put that in there as well, and I give these sources some labels and so on. That was the source part. Then for the receiver, I'm going to put 3 receivers into the space, and I'm going to have them be spatial receivers, meaning that the output is an ambisonic room impulse response, and then we can work with that further in post-processing. So that's really kind of the fundamental steps of doing the simulation: room geometry, materials, sources, and receivers. And now let's see how we run the simulation, obviously, but also how we then work with the results to get the device-specific output. And we have this very cool functionality for rendering the device-specific output. So we need to run the room simulation and get out these very high-fidelity, high ambisonic order spatial room impulse responses, but we only need to do that once, and then we can, in post-processing, render the device-specific output. We can change out the device, we can rotate the device, all in post-processing very rapidly. And this way you can augment data and so on very quickly. And the way to get the device data into the SDK to then mix with the spatial room impulse responses, there are 3 ways. If you have a measured HRTF or DRTF, then you can import that in a SOFA file. You can also import a device CAD, and Treble will simulate that for you, and you get the DRTF just directly from the CAD. I'll demo this in a second. Or if your organization has a library of some kind of receiver devices, that is, then you can also use that. Okay, so here first I show how to import, which would be this path here. From a SOFA file, it's really just a few lines of code to import this into the SDK. We've already run that block, so we've imported this KeyMar mannequin. It's from a database from online, but we on added 2 other devices as well. On the one hand, sort of a mannequin with a headset on it, and the headset has 2 microphones on each ear, 1, 2, and then here as well, 3, 4. And then something of a fictional smart speaker, which has 3 microphones on the top here. And then we are going to run the room simulation and then work with these devices in the post-processing. And I fetch these devices here. This guy here we call DJ Hats, the smart speaker, and the KeyMar mannequin as well. For running the room simulation, I can set some settings. For example, I say that the ambisonic order of the spatial receiver should be order 32. It's a very high order. The Treble offers this capability of working with these very high order ambisonic impulse responses, which is needed if you want to get physically correct results, device-specific spatial results for a broad range of frequencies. We can set some other settings of the solver. You can also just use default settings, but we're just showing an example here. And then we create the simulation definition. We tell it to be a hybrid simulation. So for low-mid frequencies, we do a wave-based approach. For the high frequencies, we use geometrical acoustics, switching between the two at 4,000 Hertz. We tell it to simulate long enough until there has been 20 dB of energy decay in the room. We put in these receivers, sources, materials, and settings. And we can plot the setup here of this audio scene that we've now generated. We can see here something of a dinner party, you can say, where we have a couple of sources here, which can be people talking. This is the speech source. This is actually the omni source. And then two sources here, which could be some kind of distractor sources from the TV and from the coffee machine, say. And then we have three receiver positions, these spatial receivers, which we will mix with the devices in post-processing. And we can see all the materials that we assigned and so on. All right. And in order to run this simulation, I would simply run these 3 lines of code here. It takes a few minutes to run the simulation. I've already done it just to save some time. So we can simply, with these lines of code here, fetch the latest simulation results from this project. And then we can start working with the results. And I'm going to show the device-specific output for these different receivers and different receiver positions and different orientations. We use source number 1, which is the omni source here, and we're first going to look at receiver number 1, which is this guy here. And if the orientation is, or rotation is 0, 0, 0, that means the receiver is looking down the x-axis here. And I'm going to render results for DJ Hats, which was the mannequin with the headset. And we see here the impulse response. And if we zoom in on the very early reflections, or the direct sound on the early reflections, we see that microphones 1 and 2 have the same amplitude. These are the microphones on the left side. And then the microphones on the right side have lower amplitude and of course arrive also at a later time. If we then rotate the device and re-render again, we will of course see something different. Now it's microphones 1 and 3, which are the microphones on the front of the left and the right ear, arrive at the same time and with higher amplitude, and the microphones on the back of the device on each ear have lower amplitude. We can then switch out to another device, smart speaker, render that. That has 3 microphones, not 4. Now they're looking straight kind of at the source here, but maybe we can have the same orientation, so looking down here, but go to this receiver here, receiver number 2 instead, but using the smart speaker and re-render. Then we see that the impulse responses, or the direct sound, arrives at different times because it's coming kind of from left to right across the microphones on the device. We can look at the Keymar mannequin as well. Which is just the binaural signal. And then of course the ear facing the source is louder than the ear on the other side, essentially. This might look slightly more noisy than the results before because the Keymar HRTF is a measured HRTF, whereas the smart speaker, and the headset was simulated DRTFs. We can look at the frequency response, of course, as well, and yeah. So this is basically a simple example of showing how you can generate device-specific output in complex audio scenes very easily with very high precision, and then use that to virtually prototype hardware or machine learning audio algorithms. And now maybe a natural question would be to ask, how accurate are these simulations? It looks pretty cool, but is it really matching reality? And the next step here is that we're going to show a quick benchmark comparing measurements and simulations for these kinds of scenarios. All right, let's dig into this particular validation case here. It concerns a small or sort of small to medium-sized room of 80 cubic meters in size. It's a room here in Reykjavik, which we have measured in great detail and then used for benchmarking simulations. And we consider the room under different conditions. First of all, being empty, but with varying levels of reverberation by having varying amounts of absorption on the walls. Then we took 10 tons of bricks into the room and kind of laid them around in random positions to really make the geometry of the room very complex. But the reason we chose bricks was to still keep the material properties relatively simple, but very complex geometry. And then finally, we went sort of the whole way, where we both have complex geometry and complex material properties by introducing a lot of sort of traditional furnishing like sofa and chairs and tables and things like that into the room. And we measure both mono and binaural room impulse responses. The binaural impulse responses were measured with a KEMAR mannequin. And it's a bit of a spoiler here, but basically in all cases we see a very good match between measurements and simulations, but let's of course dig into the details. And in this case, we ran a wave-only simulation in all cases. That's very practically doable in a room of this size. Okay, let's first look at the empty room. It looks something like this. We excite the room with a directional sound source, and of course in the simulation we also use a directional sound source. We consider a variety of source and receiver combinations, and in the simulation for the receiver, when it comes to the binaural part, we use this approach that I just showed earlier, where we simulate a spatial room impulse response, and then in post-processing we mix the spatial impulse response and the HRTF to get the binaural or the device-specific output. But if we first look at the mono results, here in the time domain, we see an excellent match between measurements and simulations. The early reflections are captured very nicely, and the overall energy decay as well. If we look in the frequency domain, also a great match. The low to mid frequency modal behavior is captured nicely, and the high frequency trend is also captured very well. Energy decay at different frequencies looks very spot on. It of course helps that in this case we know the material properties of the wall materials quite well. So there's good input data into the simulation. These are acoustic parameters. This is T20 and this is early decay time. Great match observed. Note, for example, here in the mid frequencies, this interesting increase in reverberation. This is due to a 2D sound field living between two hard parallel surfaces, which is very well captured in a wave-based simulation. And then the binaural results also look fantastic. This is the right and the left ear for one particular source-receiver combo. Clearly the receiver's right ear is facing the source. We can also have a listen. Here we have an anechoic recording of a speech signal and a music signal. And then we've convolved that with the binaural room impulse responses, both the measured ones and the simulated ones. And let's have a listen. First, the anechoic speech sounds something like this.
Noise and poor acoustics have been shown to be a major factor impacting our health, well-being, and productivity.
And then in the measured room.
Noise and poor acoustics have been shown to be a major factor impacting our health, well-being, and productivity.
And the simulated room.
Noise and poor acoustics have been shown to be a major factor impacting our health, well-being, and productivity.
And for the music, first anechoic. measured room. And the simulated room. I hope it comes through clearly in the webinar and in stereo and all that, but I can at least say in my totally unbiased opinion that they sound actually very similar. Okay, now we turn to the complex geometry case where with all the bricks, the 10 tons of bricks, it looks something like this. So the geometry of the room has been modified substantially, and it's a much more complex case, you can say. But the results look, I would say, equally good as before. Here we're looking at mono results, time domain, excellently capturing these early reflections. Room modes, again, captured very nicely, and the overall high frequency trend as well. Energy decay still looks absolutely spot on. And binaural results with the Keymer mannequin also look fantastic. Look at these early reflections here and the difference between the right and the left ear. Same with the frequency response, the room mode behavior here, and the high frequency trend, the ear canal resonance, and these things are all absolutely captured in the simulation. And finally, the furnished case, where it looks something like this. And yet again, measurements and simulations match up very well. This is one particular source receiver combo. Here's another, looking equally good. Energy decay, very good. And binaural results look excellent as well. Here in the frequency domain. So this goes to show that the Treble simulation engine is really capable of producing real life-like quality audio data, simulation output, device-specific output, as you would get from real-world measurements. Now let's move to a different thing. I'm going to show a new feature. It's a bit of a, so actually everything we're showing in today's webinar is production-ready features available to our customers. We will also share these notebooks that we're demoing with everyone who's signed up for this webinar, so you can give them a spin yourself if you're either a customer or have a free trial. The only thing which is sort of a coming soon thing is what I'm going to show next, which is the capability of generating a DRTF or an HRTF from a CAD file. Let's take a look at that. And we're going to demo a prototype of it here. So the workflow here is as follows, that the input to this DRTF generation from CAD is that you import the CAD of the device, for example, a smart speaker. You set some settings on this DRTF generation simulation, and then a free field simulation is run where sound is radiated actually from the microphone positions of the device to a sphere of receivers around. So you essentially have a transfer function from all different incidence angles to all the different microphones. The results of this simulation are then essentially converted to the spherical harmonics domain and stored as a DRTF. You can then store it in the library of devices your user or your organization has. And then, of course, you can use this just as I did before in simulations, in post-processing, in rendering, and so on. So let's take a look at this part here in this prototype. First part, as usual, is just sort of to initialize and log in and so on. Once that's up, then I'm uploading a CAD model, in this particular case within a 3DM file, of a fictional smart speaker that we've made here, which looks something like this, where the speaker is here and the microphones are here. I then set up this free field simulation, setting some settings such as the frequency range I'm interested in, the number of points on the sphere. There is some relation between how many points you have and what ambisonics order you use. This can be seen in our documentation. And then I specify the location of the different microphones on the device, essentially. And that's really all that's needed to set up and run the DRTF generation simulation. Then I can simply run it here, or if I've already run it, which I've done in this case, then I can fetch the results from some IDs and plot and explore and so on. So this is the setup of the DRTF simulation. So the domain is a sphere here. The device is in the center, and then there is all these receivers around. And if I zoom in here, we can see the microphone positions here, and then we simulate essentially the free field response from all these microphones to all these receivers on the sphere. And that's then what makes up the DRTF dataset. Once it's the simulation is run, we simply run this create DRTF command, and that's already been run, and we can add it to our library of devices. And that's it. Then you have your DRTF, good to go, ready to augment data, create 100,000 room responses with this device in 10,000 different audio scenes or whatever you would like to do.
Hello, my name is Georg Götz and I'm audio research engineer here at Treble. And in the following two notebooks, I want to tell you how you can use the Treble SDK for your machine learning efforts. As Finner already showed you in the previous notebook, we have conducted measurements in this room, and we have matching simulations where we were very careful to match the measurements as close as possible. In this notebook, I want to show you how we can use the simulations and compare those with the measurements while evaluating on a neural network for speech distance estimation. The outcome there is that we can show that when the measurements and the simulations match very closely, the same applies to the machine learning evaluation. So instead of running lots of measurements, you can also run the simulations with the Treble SDK and get equally good insights about your machine learning model performance. And I want to start by just reading in the simulations that we have done, and I can show you once again how this looks like. In here we have a couple of source receiver configurations, but because these were done similar as the measurements, we only have a couple of them. In fact, it's only 20 source receiver configurations because doing the measurements just takes a lot of time and it's kind of costly. That's why we only have so few points at first. And what we want to do is we want to do speech distance estimation, as I already said before. And you can think about this similar as in this application scenario here in the picture. We have somebody who is speaking with a friend, and the friend, for example, has some AR glasses or some other wearable that has a microphone on it. And the person is speaking, and we record the speech with the microphone. And from that recorded speech, which might be, first of all, quite noisy because we have background noise in there as well, but most importantly, it is reverberant because we are usually inside of rooms. And based on that reverberant, noisy speech, we want to estimate the distance between the speaker and the listener. And this information is very important, for example, if we want to run some speech enhancement or de-reverberation algorithms on the AR glasses or on the wearable device. And I want to use the following neural network to showcase how we can use the Treble SDK and the simulations for evaluating a neural network. This network was proposed in this paper that you can see referenced here. And what we're doing to evaluate this network is that we have dry speech signals, which we take from a speech database, and we have either simulated or measured room impulse responses. And if we convolve both of those together, we get reverberant speech signals, and then we can also add background noise to them to get our noisy reverberant speech that we would capture with the microphone on the device. We then import this noisy reverberant speech to the neural network, and the network tells us the estimate of the source receiver distance. Of course, we also know a ground truth in this evaluation scenario because we have set this up as measurements or as simulations, and then we can compare this ground truth distance with the estimated distance from the network. If we do this over the entire evaluation data set, we can calculate a mean absolute error. And in this case, for the figure, we of course only have one item that we compare. Therefore, the mean absolute error is just the difference between the ground truth and the estimated distance here. And what we're doing now is that we are reading a pre-trained checkpoint from this model. So it's really important to emphasize that no simulation data or no measurement data from our side was used in training this model. We are just using the data now to evaluate how does the model perform. And to do that, we first have to calculate the ground truth for the source receiver distance. And we do this quickly here for the measurements, which is just one for loop where we calculate the distance. And as soon as we have done this, we can set up our PyTorch dataset for the evaluation. And as I said before, in this demo, we have two evaluation datasets. The first dataset is using the measurements from the lab environment, and the second dataset uses the Treble simulations that are replicating the measurement setup as closely as possible. So we're reading in both of those datasets, and now we can already start to evaluate the performance. So first we evaluate the performance on the measurements. And if we do this, we only have a couple of items here, so the evaluation is quite quick. And we see that our mean absolute error is 1.57 meters. And now, after this is completed, we can also run the evaluation on the matching simulation. And we see in this case, our mean absolute error is 1.54 meters. And already by just looking at one number, we see this is a very close match, but one number can of course also be a bit deceiving. That's why we have a closer look at all of the evaluation responses. And we see here on the left-hand side all of the evaluation outputs for all of the 20 measured and simulated source receiver configurations. And on the left side, we have a box plot summarizing all of those for the Treble simulations. And on the right-hand side, we see all of the responses from the measurement. And we see both of those box plots match very well. So we can say that the evaluation performs equally well on the Treble data as on the measurements. And we see a similar trend if we look at all of the items that we get out of the network and have a look for each of those, what is the evaluation error on the Treble data and what is the evaluation error on the measured data. And we see a very clear tendency that they coincide. But now what we can very easily do with the simulations is that we evaluate on more receivers. So what you see on the left picture here is what we have done so far. We have only a handful of source receiver configurations that we measured and simulated. And now we might want to have a closer look at our network and see if the network also performs equally well at other source receiver configurations. Doing this on measurements can be a bit difficult, time-consuming and slow, because whenever we move the microphone or the sound source, we have to do this manually, and this is a lot of work. Doing this in simulations, on the other hand, is very easy and straightforward. We just add a couple of more lines of code and add more source receiver configurations to the simulations. And there is also the added benefit that the simulations are very, very reproducible, as opposed to the measurements, where you also have to be very sure to measure your source receiver configuration and especially the positions of your sources and receivers very accurately. So let's have a look at another simulation that we ran from the same environment where we added more receivers. And as you can see here, we have now added very many receivers in there, and they are on a very dense and fine grid of receivers throughout the room. So by using this simulation, we can get a bit more, or actually a lot more comprehensive overview of how our model performs on this specific task in this specific room. So let's set up the dataset again and run the evaluation once again. And because we have now so many source receiver configurations, this takes a bit more time. But this is also then down the line very interesting for us because we have more receiver configurations. We have just a better overview of how does the network perform. So let's wait until this completes. All right, the evaluation completed, and we see now a mean absolute error of 1.62 meters, which is still very similar to what we saw before, but we can also now, of course, have another closer look at the results. And we see here on the left side the treble simulations with only few data points. In the middle, we see the measurements with the matching data points. And on the right side, we see the treble simulations where we have a lot more receiver positions in there. And we see, of course, there are similarities between all of those, but what is very clear as well is that we have more receivers, and some of them seem to be outliers where the performance of the network is not as good as for the 20 selected points that we were able to measure. So this is, of course, very interesting for us because without having to do lots and lots of measurements, we get a lot more information about the performance of our model. And now we can also easily have a closer look. What are problematic positions, for example? And now I'm plotting the source receiver configurations with the 20 highest errors. So these are the 20 cases where the network performs the worst. And what we can see here is that they are mostly situated here, close to the bricks and also very close to the sources. And that might indicate that the network has some difficulties performing at such locations. On the other hand, many of the remaining grid positions, for example, here in this open space, do not seem to have these high errors. And that's indicating that the network performs very well on these cases already. So if you want to now improve your network performance and maybe get the last bit of quality out of your network, you would have a closer look at these configurations and see how your network or your algorithms could work better in these cases. And now we've seen that we can very easily add more receivers to a simulation and increase the evaluation dataset by using this. But in the Treble SDK, it's also very straightforward to add more rooms to your evaluation dataset, add different furniture configurations to your dataset, and just overall have a larger and more diverse dataset for evaluation. And everybody who has done measurements so far knows that doing a similar things with measurements is a lot more difficult. I can talk from my own experience. I have done a whole summer of running measurements in a single room where I moved furniture around all summer. And I can tell you that this was a lot of manual work. Nobody really wants to do this. So using the Treble SDK, you can simulate a data set similar to this one with just a couple of lines of code and get very reproducible and high quality results in this way. All right, in the previous notebook, I showed you how we can use simulations from the Treble SDK to evaluate your neural network. Now I want to do something else. I want to actually simulate a larger training data set and use that data to train my own network. So I'm not using the previously loaded checkpoint that we used in the previous notebook, but I will actually use our own simulation data to train the network from scratch. Everybody who has done some machine learning training before knows in order to make the network generalize well to other and quite diverse conditions, we have to also have a diverse training data set that covers many degrees of freedom. Because room acoustic data sets are usually quite complex and can vary with various degrees of freedom, as seen here in this picture. For example, we can have different source-receiver configurations, as you can see here. Sources and receivers placed at different positions, but also they can have different directivities. Then we can also have different room volumes. We have small rooms, larger rooms, rooms that are somewhere in between. And we can also have different room shapes because, of course, having only shoebox rooms is very easy to do, but typical real-world rooms have more complex shapes, and that's why we also need to cover those. Additionally, we want to have different absorption properties in the rooms. We want to have very reverberant rooms, then rooms that are maybe not as reverberant, and also we want to have different placements of those absorption materials. So we want to maybe also have material properties in a way that some of the walls are very absorptive, whereas others are not and have a bit of a non-uniform absorption. And finally, what we also usually want to add into our datasets is different scattering objects, because in the real world, rooms are rarely empty. Usually, we also have some objects in there like chairs, beds, or tables. So we can see that there's quite many degrees of freedom in room acoustic datasets, and in this notebook, I want to show you that we can cover all of these with simulations from the Treble SDK. So to do this, I start by setting up a project, and I want to start with a couple of generated rooms. As you can see here, we have different shapes of rooms that we support. And in this notebook, I want to show, for example, L-shaped rooms, T-shaped rooms, U-shaped rooms. And in the Treble SDK, we have functions for all of those to automatically and randomly generate those. So you can see here all of these different A, B, C, and D parameters, for example. These are all parameters that we can randomize over to generate random rooms. And in this notebook, I will generate a total of 200 rooms. And I will show you here the functionality that we have included in the geometry definition generator, where we can create these random rooms very quickly and efficiently by randomizing over the parameter ranges as we specify here. For example, that we want to have our side A of the U-shaped room between 1.5 meters and 3 meters. So let's do this and generate 200 rooms. If you don't want to use these pre-made functions to generate rooms, you can also just specify a floor plan as a polygon and then extrude the floor plan to a certain height to get a polygon room. This could, for example, look something like this. All of the rooms that we've seen so far were pretty empty. So this is, of course, maybe a bit boring. So let's add a couple of objects into the rooms. Also there we have you covered. We have a geometry component library, and you can see here we have a couple of different groups in there, for example, tables or beds or sofas, and all of them have already a couple of objects in there. What is very important to note here is that this database is being worked on, and we will get more of those objects very soon. So let's start with one of the sofas. This looks something like this. And already here you can see, of course, this is not a sofa that I would put into my flat, but it's actually one that is optimized for room acoustic simulation. So you have nice and flat surfaces, and it's just kind of easy to use. Let's place the sofa now in our room, and we see, okay, we have our polygon room and we have the sofa in there. Maybe let's add a couple of more chairs. The chairs look like this, and we just add 3 of them. And now we see, okay, we have our polygon room, we have 3 chairs. This will not win an interior design award, but this is something that gets us started. If you don't want to place these furniture objects yourself, we can also randomly add them to the rooms. And this is what we're doing now. So in this case, we use our geometry component placement, where we can say we want to place, for example, a table or a chair or a sofa, and we want to have a certain count in each room, which is usually the maximum count, because sometimes the rooms can just be too small and we don't fit all of those in there. But then we say, okay, they can have certain angles. For example, we want to orient the tables in 90 degrees angles. And they should have a minimum distance from other objects in the room or from walls, something like that. And we will now do this and populate all of our 200 previously generated rooms with furniture. And as you can see here, this is taking a bit of time, but those are now randomly placed into the rooms. All right. Now that this is completed, we have placed random furniture in all of the 200 rooms that we previously generated. Let's have a look how this actually looks like. And we can see here we have now our U-shaped room, and our objects have been placed there. So we have an armchair, we have some chairs in there, we have 2 tables where, in this case, of course, as I said, we optimized them for acoustic simulations, so they don't have legs. And then we have also some boxes, for example. We can also have another look at a second one. In this case, we have a shoebox room with a very socially introvert design, where you can just look at a corner and sit down on the chair here. It doesn't have to make a lot of sense, but we have added a lot of geometric detail to the rooms now that we can start to simulate. And now, if we don't want to use these rooms that we randomly generate ourselves, we can also use the database of rooms that is included in the SDK. And this database of rooms actually has, in total, more than 10,000 rooms in there of different categories that you can see here. So we have meeting rooms, we have classrooms, bathrooms, and so forth. And we can really choose quite nicely from these categories and from this database. And that's what I want to do in this notebook now as well. So previously we have 200 randomly generated rooms, and now I want to add 100 rooms more. So we pick 50 living rooms and 50 meeting rooms randomly from the database. And if we want to have a look, how does this room look like, we can do that. And we see, yes, this is a living room where we have a nice sofa in there and some armchair in there. And we have some table with chairs as well. And what you can see here as well is actually the suggested positions. And you can see here we have suggested positions at the dining table, for example, but also then at the armchair and the couch and so forth. And these suggested positions will be very useful for us later, because at these positions we can, for example, place sound sources or receivers. And this way we can place them at positions that are actually meaningful for that scene. What I want to do now is I want to randomly add materials to all of the layers. And once again, we see here the material library that Finner already mentioned. And we randomly place the materials at all of the 300 rooms and make sure that all of the material assignments are within a Sabine estimate of 0.4 seconds and 1 second. So now that we assigned the materials for all of those 300 rooms, we can have a look, how does it look like, and we can see we have generated a T-shaped room, and we have assigned the materials, and we also assigned the materials to the furniture that we added. Now I want to go back to this application scenario that I already mentioned in the previous notebook. So we want to do speech distance estimation. We have some speaker talking with somebody else, and this other person has a headset or AR device, for example, on it with microphones, and we want to estimate the distance between those two while we have background noise. To simulate this, we will add a couple of directional speakers in our scene, and we will add a couple of noise sources, which are omnidirectional sources, into the scene. In addition to that, we will add a couple of receivers, and that will be actually spatial receivers in this case, second order ambisonic receivers, but we could also, if we wanted to, go up to 32nd order of ambisonics. So what we are doing now is we're placing those speech sources randomly inside the scene, and what we are doing is we place them according to some rules. And those rules are that they should be at least 0.5 meters away from every surface in the room, so for example furniture, but also walls. And they should also be at least 0.5 meters away from other points that we've generated. We are using the speech directivity now and use the functionality of the SDK, which is the generate valid points. And that makes it very easy to generate those random rooms according to the rules inside all of those 300 rooms in just one for loop. Now that we included the speech sources, we will also add the noise sources into the scene. And once again, we use a point rule set there where we make sure that all of the sources that we place are at least half a meter away from all of the surfaces in the room, and also from all other points that we're generating. But then we also want to make sure that all of those noise sources are at least half a meter away from the speech sources. We generate the omnidirectional sources in there and add all of them to our rooms. And finally, we will set up grids of receivers for the generated rooms as well. So we have this functionality in the SDK that is called generate valid grid, and there we can just say that we want to have a uniform grid with a certain resolution in X, Y, and Z, and we want to also make sure that all grid points that we generate this way have, for example, a minimum distance to the surfaces in the scene or a minimum distance to the existing points in the scene. And in this case, the existing points are all of the previously generated sources, and we just make sure that all of our receivers that we generate are at least half a meter away from them. And finally, I want to show you that we can also use the position suggestions from the material database, as I mentioned before. So what I'm doing here is I will add in the database rooms, I will add my receivers at positions that are called either chair, couch, or table, and that will make the receivers be located at positions where people are usually sitting, for example, which is also nice to have a bit more informed positions for the receivers. And now that I've done all of this, I can set up my simulations and add them to the project. What I'm doing now is I'm setting up hybrid simulations with a crossover frequency at 500 Hertz. That means up to 500 Hertz we use the wave-based solvers, and above 500 Hertz we use the geometrical acoustic solver. And by doing this we make sure that we have a significant range with the wave-based solver, which gives us very highly accurate results. And now we have all those simulations added to our project, and we see in just a couple of minutes we generated quite many simulations with quite many sources and receivers in here. And if we want to kind of double check how do these look like, we can also still have a look at the simulations. And we see here this is a fairly small room, so we don't really have a big grid in there because of our rules, which were quite strict. But we have our sources in there. We have a couple of furniture objects. This is looking pretty good. We can also have a look at another example where now we have actually a significantly larger room. We see we have added a sofa in there, we have added a table in there, and we have a nice grid of receivers in addition to the sources that we have placed. And we have all the materials assigned here as well. And now we will have one final look at one of the database rooms, and we see very nicely here the receivers are actually placed at the table, so we see people are sitting at the table, whereas the sources are actually placed randomly in the room. Let's quickly estimate the runtime of this whole project, and we see here now for all of the simulations what is the estimate. And actually for simulating this entire project, which contains 20,500 room impulse responses, this would only take us something like 4.5 minutes and set us back 51 tokens. Of course, I said before, we have this knob where we can control when do the wave-based simulations start and when does the geometrical acoustic solver take over. If we were to run the same project only with geometrical acoustics, the whole estimate would look quite different. So we would be even faster. All of those simulations would run in approximately 40 seconds, and we would only have to spend 7.6 tokens on the entire dataset. Whereas if we use a 4 kilohertz crossover frequency, this would take, of course, significantly longer because we simulate a wider bandwidth with the wave-based solver, so it would take 6 hours and 20 minutes and set us back around 10,000 tokens. But once again, we have 20,500 room impulse responses in the dataset, and at 4 kilohertz crossover frequency, we also have a very large range where we use the wave-based solver and therefore get highly accurate results for our machine learning training. And what we can do now is just start all of the simulations that we have in the project, and these are 300 simulations, so let's do that. The simulations have started now, and what we can do is that we have a look at the progress now. Because what is happening is that we are now sending 300 simulations of 300 rooms and then times 5 sources, so in total 1,500 simulations. We send those to the cloud, and all of them can run in parallel. And that's what we're seeing here now, that we have quite many of those, actually 1,000 of them already in progress, whereas we have a couple more of them queued because this is my current concurrency limit. If we now let this run for a while, we would see that the simulation slowly but steadily complete. I don't want to do this now, but instead I want to use the simulations that I have already completed before the recording and use this now in the training. And once again, I want to show you now this plot where we see how does our network for the speech distance estimation work. I don't want to repeat this again, but what is important to note now is that now instead of calculating the mean absolute error as an evaluation matrix, we use this as our loss and actually feed it back to the neural network to calculate gradients and train the neural network. So essentially, to summarize, this notebook showed you how you can generate a very large and very diverse room acoustic dataset for machine learning training, and all of that used the hybrid solver that you can use from Treble, which has highly accurate simulation results.
I am Daniel. I'm the product manager of the Treble SDK, and I'm going to show you a few use cases here at the end. So the first one is this parametric study where we examine a studio, this one here, and we're going to place subwoofers in different positions and evaluate which one is the best for the coverage and for the sort of typical listening positions in such a studio. Then we're going to put in 2 full range speakers so we can have a nice stereo experience in this recording studio. What powers this parametric study is this very, very nice feature that is coming with the Treble 2.0 release. We call it the boundary velocity feature, and it basically enables you to model any speaker that you may desire. You can think of a speakerphone on a table, or a smart speaker, or some floor speaker in a living room, or these full range speakers, a subwoofer in this recording studio. Essentially, you have a CAD model, or we help you generate a CAD model, and we take care of anything for you in terms of doing this boundary velocity. Essentially, you just have to specify the membrane that vibrates, and then we assign some velocity to that, so then it's like a piston moving back and forth like a real loudspeaker, and then some simulation settings so we can get the correct directivity and source correction filters and so on. From that, we create a free field simulation and a anechoic simulation of the device, and that will give you some free field results such as source correction and directivity. We import that into a submodel library, and then you or anyone in your organization can use that when you define sources and create simulations. So here I am analyzing a recording studio, but maybe next week a colleague of yours is doing a living room and they need a subwoofer model. Well, then they can access this shared submodel library. You already did all the work. They can just import that into the simulation and they have a subwoofer. So let's get started. First, I just log into the SDK and I get this project, subwoofer placement. And then the first thing I do is construct the subwoofer. So here I make a free field model based on a CAD geometry. Here I import a 3DM file of a subwoofer. And then this gives this free field model where we see the subwoofer in the center and this kind of anechoic sphere around it. The next thing to do is we create this free field simulation. So if you recall from the flow diagram I just showed you, we have a CAD file and then we have some simulation settings. Those two combined gives us this free field simulation. So that is essentially what we're doing here, specifying the membrane that vibrates and so on. So that will look like this. So suddenly there is a sphere of receivers around the device that we need. You can see the membrane here and so on in the plot. And then the last step in sort of defining this boundary velocity submodel that can then be injected is to add it to the submodel library. And that sends the CAD file of the loudspeaker. It sends information about the directivity and the source correction filters needed. What this enables you to do is now I can inject this CAD model into any room. It uses the actual CAD model in the wave solver, accounting for diffraction of the edges of the box and so on. But we also have the directivity information, which means that if I choose to run a hybrid simulation, I can do this account for the CAD geometry of the speaker up until the cutoff frequency of the wave based, and then above that frequency we use the directivity and model this as a directive point source, which is in my mind a very strong feature. You can, since it's a CAD model, also place it very freely in the model. So I could place this source on a table. In this demo, we place it on the floor. It could also be on the wall. So with the source ready, we can go ahead and define the room. So here I use the import functionality of the Treble SDK to import this studio control room. We use the 3DM file here, and we do a check to see if the geometry is valid. We do that on all imported geometry, so we check if it's watertight or there are any other errors in the model. And here we see it. Yeah, it consists of a couch, this mixer in the front. Can maybe use this here to highlight. We see some windows, We have these rear acoustic panels that we're going to work a little bit with. So I'm going to demo how you can build your own absorbers in the treble quite easily using our material builder. So essentially I just need to define 3 parameters to create a new absorber in treble using this porous material builder. So I define a porous layer thickness of 50 millimeters and a flow resistivity of 10,000. And then finally, I also want to have an air cavity behind this porous layer, and I say that in this case it's 100 millimeters. All the materials are then terminated with a rigid backing. I can then go ahead and run this code. I've built the material and added to the material library, and we plot it just to verify that it looks as we expect across frequency. We can see the absorption coefficient here, but also the reflection coefficients over here on the right. The next step in setting up a simulation is that we want to pair the layers in our room model with materials. So we take, for example, the couch layer here, and we pair that with upholstered seating, well upholstered. And we use the material library in the Treble SDK to find this material. Similarly for the walls, we find some gypsum material that we like, and so forth. Most of these materials, except for one, we just use the Treble library that's free for everyone. That is a user of the Treble SDK. We have hundreds and hundreds of materials that you can use for the walls, ceilings, carpets, and floors, and so on. And then in the bottom here, we see we have this new material that we assign to these rear acoustic panels. As a quick sanity check, I do a Sabine reverb time estimate here. Generally, a recording studio has to be pretty dry, so we want it to be between 0.2 and 0.5. And here I see it's 0.38, so we're quite satisfied with that, and we can continue to define the simulation. In this case, we choose to set up 5 receivers, 3 at the PA, on the mixer, up at the front, and 2 in the couch. I'm using spatial receivers here because we want to later on import a HRTF, a measured HRTF in this case, so we can render that device with the spatial impulse responses and then get the binaural IRs, so we can listen back to how does this recording studio actually sound at the end of the simulation. So with the receivers in place, we can go ahead and define our sources. This is a parametric study, so we're going to look at quite a few different subwoofer placements. So what I'm going to do here is first I will define in what positions do I not want a subwoofer, and we don't want it in the middle of the room because then you're just going to trip over it and it's not going to be a super pleasant experience. And secondly, I don't want it in front of the door because I want to be able to open and close the door. Then we use this generate valid grid function that takes in we define some resolution in the horizontal plane with X and Y. And then we define a height of the subwoofers. And then we include these positions we just defined in the existing points to ensure that we don't define any sources here. One thing is the XYZ position of these subwoofers, but we can also specify a rotation. In this case, we choose to have an azimuth angle such that all subwoofers face towards the center position in front of the mixer. With sources, receivers, and materials defined, we can go ahead and create a simulation. So we do that by making a simulation definition. Here we specify that we want to run a full wave simulation. We want to use the control room that we imported with the material assignment we just did at a crossover frequency of 400 Hertz. So we can go ahead and plot the simulation definition. I'm just going to hide the ceiling here so we can take a better look inside. We have 21 different subwoofers placed along the edge, and then we have these 5 spatial receiver locations here. And we're going to run this in the cloud. If I had to run this, it would take a handful of minutes probably. Here for, you can say, the flow of the demo, I'm just checking here if there's already a simulation in place, and there is, and we can then continue with those results for the parametric analysis. So here I'm fetching the results with this get results object and putting them into this. What I'm then going to do is we have defined a cost function that essentially scores the different subwoofer placements. It takes into account the evenness of the frequency response. I don't want a subwoofer placement that causes a large dip in my frequency response that could indicate some modal behavior going on that's not very pleasant and something that you want to avoid. We're considering that there is the sort of a good energy balance on either side of the 100 Hertz mark. And then finally, we are considering that the subwoofer placement should also have as little variance across all 5 listening positions as possible. Doing that here. And I mean, we are basically now in the post-processing stage, so I can go ahead and evaluate the cost function in all the 21 different positions. It's very fast. We want a slow cost function as possible. So we immediately see that to the right of this mixer, there is a very good placement candidate here. But we also see over here towards the right wall that there are some quite good placements here as well. Probably due to the walls having quite a bit of absorption here. Whereas we see over here, it's not looking so good, probably due to this large rigid surface without absorbers over here. The worst subwoofer placement is then right under the PA. We can see that here, close to 1, or 1 because we normalized the cost function. I can then do some further analysis on the impulse responses, or in this case, I will just jump to the frequency response essentially. Here I load in the worst and the best woofer placement essentially. Just gonna quickly limit the frequency axis here, so we look at, you can see what we actually simulated, and we can see, for example, so the blue curve is the worst placement and the green is the best. We can see here around 40 Hertz we see a dip of more than 20 dB, and we also see quite a lot of unpleasant dips here, which is something that you want to avoid, where the green curve is much more even, indicating that this is indeed a quite good candidate for a subwoofer placement. So we have found a good place for a subwoofer. Let's put in a full range stereo speaker system as well. Again, using the boundary velocity source. This time I'm going to go over it a bit more quickly. I do want to highlight that before we imported a CAD model of a speaker, here I'm going to use the component generator in Treble, which is very straightforward if you want to have a quick CAD model of a loudspeaker in your model. So I'm just going to define a width, depth and height here, along with a membrane diameter and a few other settings. I can then generate a free field model from that, and that can be used again. So now we have the CAD model again, and then we define some simulation settings down here. We can then do the free field simulation, and from that we can construct this boundary velocity source submodel that can then be loaded into any simulation. And naturally, in this case, we're going to load it into this recording studio. So here I'm defining the 2 speaker positions for the speakers. Going to define also again an azimuth rotation here, so it is pointing towards the center of the mixer. And we can then plot the simulation definition of these 2 full range speakers here. I think the most important thing here to highlight is now that we are doing a hybrid simulation, not a full wave. So that's again one of the strong suits of this boundary velocity. It caters to, you can say, the whole package basically. So up to 1000 Hertz, I'm using the injected geometry. I'm doing a full wave-based simulation on that. But above 1000 Hertz, I'm using this directive point source. We can extrapolate the directivity from this free field simulation we did, and then we can use that to do a GA, geometrical acoustics source, and run a hybrid simulation that will be faster to run. So here we see the simulation definition with the 2 speakers in front of the mixer pointing towards this center position here. I can then add the simulation to the project. Again, I have already run it, so it checks, okay, it's not necessary to run this again. And I can then work with these results in the oralization part of this demo. Before I do the oralization, I want to create an HRTF device essentially. Here we used a message HRTF on a KEMA mannequin. I apply the HRTF device on the subwoofer IR, but also of course on the left and the right channel. Then we have added the functionality to do filtering also on IRs. So we have a filter object that works on the IR object, in this case on the device IR, but it could as well have been a mono IR or a spatial IR. For the woofer, I want to have a low pass filter, so I define a cutoff frequency of 200 with an order of 6 for the Butterworth filter. And then I also include a gain filter with a 0.3 to ensure that the woofer and the full range speakers have the same level. For the full range speakers, left and right channel, I use a high pass filter, also with a cutoff frequency of 200 to have the correct mix. And then it's very straightforward to combine the device IRs here. So for the left channel, we use the subwoofer plus the device IR for the left channel, similarly for the right channel. We can then compare the filtered impulse responses. So if we look at the frequency response of the full range speakers, we can see that we apply this high pass filter here with a crossover frequency of 200, and we see it behaves exactly as we expect. So then we can convolve these device IRs with an audio signal. I'm just going to do that here. We are standing here in the center position of the recording studio and listening back to how does it actually sound. So I hope this demo showed that it's very straightforward to do very advanced modeling in the Treble SDK. We import this loudspeaker geometry, we assign boundary velocity to it, we parametrically place it in the recording studio with fast simulations. We get the modal response and we can make quick decisions of where should I place this subwoofer in the room. Then we add in full range speakers with a hybrid simulation, and sort of we can analyze the room and see, is this really a good fit? And it seems it is. And you can do this over and over again to converge to a result that you are happy with. Okay, next demo. Something different, but not completely. We're still in sort of boundary velocity domain, but very different environment than the recording studio we just visited. So this is a car cabin, and the initial geometry was obtained through a LiDAR scan, thanks to a very good collaboration with our friends at Audio. So thank you very much for that and the good collaboration. We did a scan of this car and then imported that LiDAR scan into a CAD tool for further processing, sort of putting in some more details and using the LiDAR scan as a sort of as a background to essentially make the car model from. And then that car model can then be uploaded into Treble to perform an acoustic simulation on. So what we're going to do here is sort of modeling an infotainment system in a car, so a multi-way speaker system. We're going to do a 1 kHz simulation of a woofer in the trunk, and then a spatial receiver in the driver's seat. And we're going to do that fully wave-based up to 1 kHz. Then we're going to do a KEMA rendering as we did before for oralization purposes. And this time the filtering will be done with a TIL-small parameter model, lump parameter model. So we are going to do like create a physically informed filter here. And then we're going to do an 8 kHz simulation of a tweeter pair situated in the car doors. Also with the spatial receiver obviously in the same position at the front seat. And this 8K simulation will also be fully wave-based. We're going to get some spatial impulses responses from that. We will render it with an HRTF of the KEMA mannequin again, and then the tweeter response will be made from a lump parameter model here as well. We'll combine them and then do a nice oralization at the end. So for the tweeter pair, let's first log into the SDK and fetch the car cabin project here. We're going to quickly import the 3D model of a car into treble. That was fast. Look at this model, quite complex actually, and it's right here. I'm impressed every time. Sorry about that, but this is just really, really cool with the level of detail you can do in the software. Out here on the right, we see it's a very complex model. We have a lot of different layers that we have to assign materials to. So in the next step, the material assignment function is very condensed. So we use a config file actually here for the material assignment that's hidden away, but of course available with the notebook. Just gonna run this here. And then we are gonna load a tweeter submodel. So this time we're just gonna interact directly with this boundary velocity submodel library. Gonna query for the speaker name, and we have our tweeter. No further things are needed. We can just directly use that in the source list to make a boundary velocity source in the car doors. And then we're placing the receiver in the listening position in the driver's seat. So that's basically it. And then we will create a simulation definition with a crossover frequency or like an upper frequency limit of 8,000 Hertz. So then the simulation model of the car will look like this. We have the tweeters here situated in the doors, left and right, and then we have the listening position here in the driver's seat. 5 blocks of code. You have a car in treble plus a tweeter pair. Gonna add that simulation to the project, and then we can choose to run it. For the sake of time, I'm not going to, but you have this left-right channel and then this receiver. Computational time of something like this, 8 kilohertz, very high fidelity, very accurate, and very detailed model. It's 1 hour. You can, one source, one receiver is 1 hour. In this case we have 2, but the simulation time is still 1 hour because we are a cloud company. So we send the simulation to the cloud and we just spin up 2 GPUs instead of 1. And it would be the same if you have 16 loudspeakers in your infotainment system. It will still only take 1 hour to do this car in treble. We move on, and we also want a big, nice woofer in the trunk of our car. So we query the submodel library for a woofer with a 1 kilohertz simulation. We can add that to our source list, and that can then be added to the simulation definition. So this is a new simulation we're doing. We're reusing the car model, but now we are injecting a subwoofer into the trunk of the car, right here. And now we're going to compute then the impulse response from the woofer to the spatial receiver in the front. We can add the simulation to the project, and then we can run it with this lines of code. Again, we have already run it, so I'm going to press no here. So yeah, this is basically how you would compute the car cabin acoustics for the infotainment system in the car in treble. We'll now move on to the post-processing script. So this sort of emulates, okay, the simulation takes an hour, you're going to do something else. I mean, you can just continue your work. This is a cloud simulation. It's not blocking your computer or anything. It just runs on the cloud and you can do something else. So now the simulations have finished. I will log into my account again. We'll load this Kima mannequin from the device library. Again, we have to load the project we just did. We're fetching the simulations, and then we are getting the results object and putting it in this results here. Then we are rendering via the spatial IRs in the loop, giving us the woofer and the left and the right channel, so the tweeter pair, essentially. So far, so good. So last time we did these Butterworth filters to make a crossover network that we could then use for all organizations. Here we're taking it one step further to show how could you use teal small parameters in post-processing in treble, electroacoustics. And we actually have 2 different ways of doing that here. So for the woofer, we use a sort of what we call a generic model. So of course we input the membrane radius of the woofer, but then the resonance frequency, QES, QTS, and the BL factor is all you need to create the lump circuit of the woofer. So that's one way of doing it. Another way is just using directly the Thiele-Small parameters obtained through measurements or data sheets or whatever. So the electrical components here, RE and the BL factor, together with the moving mass, RMS, CMS, and then we also take into account the volume of the box of the tweeters. And then to sort of just visualize how these filters work, we create an impulse response. Just some impulse response just to show before we then process the actual car simulations with this signal. So we define a transition frequency for the woofer at 300 Hertz and a gain. And then we do a crossover network again here. So we make a Butterworth filter and that is low pass, and then we make a Butterworth filter that is high pass for the tweeter pair. Then we can go and view the frequency response of this lumped circuit. We see the frequency response here of the woofer, and then the frequency response of the tweeter here. You can then move on and then do the filtering on the device IRs we obtained before from the simulations, using the low pass filtering the woofer to design a crossover network, and then high pass filtering the tweeters. But then I think most importantly here is using then this woofer lump parameter model to filter the woofer response, and similarly for the tweeter we use the tweeter lump parameter model to filter that. And then we plot the combined response. So if this frequency response have quite a bit of information, so I'm just going to first start with the combined response. So I mean we add things together, right? So it's possible to to show basically what will the frequency response in the car be if we use these filters. Then it will look like this, and then we can start to sort of investigate the individual components. So what is the woofer contribution to this response? What is one of the tweeters' contributions, and what is the other one? And then you get this. So you can examine the individual contributions, or just look at the combined frequency response, which probably is the most interesting. Then we have a small organization example for this infotainment system. So we start by loading some car noise in, just to give you a sense for that. I'm going to play it back here. Okay, and then we are going to combine the background noise with a song, a Fleetwood Mac song, The Chain, where we're going to assign the mono signal to the subwoofer, and then the left and the right channel to the tweeter pair. Then we can organize that as well. Okay, so there was an idea of how you could do infotainment system modeling in the Treble SDK, injecting these bound velocity sources in, and then doing left and right channels, and then a subwoofer in the back, using lump parameter models to filter the response. We also have a different example. So one thing is of course modeling the infotainment system, but another thing is modeling how a conversation would be in a car. So we have an example of an SGI simulation as well, where we again will use the same car model with the same materials, and here we're going to inject an entire mannequin into the front seat, and then place receivers at the passenger seat location and also in the rear of the car. And the simulation will also be run up to 8 kHz wave-based, of course. And then we're going to look at some acoustic parameters. in this case the speech intelligibility, and analyze that. So again, we're logging into the SDK and fetching the project and so on, and then we are loading the car model in again. It's the exact same model as before. We're going to assign materials in the same manner. And now the difference comes, you can say. So that's in the source modeling. We have a scanned model of a mannequin here, typically used in many different measurement setups in cars, but also communication device modeling and headphone modeling and so on. But here we choose to use it in the car. We have this surface here. You can assign a boundary velocity source to it. So I'm just going to add that to the source list, and then at the same time we are making these 3 mono receivers, 1 in the passenger seat and 2 in the rear. And then we're going to create the simulation definition up to 8 kilohertz with the car model, and then we're going to plot that here. Five blocks of code, and we can inject the mannequin into the front seat. I think that's really impressive. Then we can use that as a speech source and compute the impulse response functions to the different receiver locations and use that for the speech intelligibility analysis. So we can quickly add the simulation to the project, and then we can decide if we want to run it or not. In this case, the answer is no. In your case, if you want to try this notebook out yourself, it will of course be yes for the first time. So yeah, now we have a simulation here, and we go into a post-processing step. Here, I'm just gonna again log into the SDK, and then we're going to fetch the project, the simulations and the results, and then we will use this plot acoustic parameters function that you can do in Treble on the results object. And in this case, we're going to do SDI between the speech source from the mannequin and then to different positions in the car. So here, I think it would be very nice to compare how's the experience of the passenger in the front versus a passenger sitting in the rear to the right. Yeah, I think that was it for the car demo. I hope you liked it. I think it's very exciting that you can not only do rooms in the SDK, but you can also upload way more complicated geometries like cars and so on. I'll remind you that you can also check out our documentation that also goes live together with the Treble 2.0 on Tuesday, where there will be plenty of examples and good documentation and guidance how to do these things and much more. Thank you.
All right, that was it for today's demos. I really hope you enjoyed them as much as we did. And as previously mentioned, we will share all these notebooks with all the signups, all the attendees of today's webinar. We have close to 1,000 participants. That's absolutely fantastic. Thank you so much for joining us. We look forward to sharing this with you, and we hope that you, if you're a customer already, that you just start using all these new features and so on, or if you're interested, then you give it a spin and try for yourself. Okay, I wanted to say just a couple of words about licensing of the SDK, and then we will go to the Q&A. The SDK license model is comprised of 2 parts. On the one hand, a fixed subscription fee, which depends on, or the amount depends on which subscription tier you go into, and then we have a usage-based fee on top, or simulation tokens. The different subscription tiers, they contain varying levels of support and training, cloud compute resources, and so on. And we would be very happy to provide you with a quote for your organization if you're interested in learning more, so just don't hesitate to reach out to us. That was it. Now let's go into the Q&A. Okay. Hello everyone. Now we start the Q&A. Thanks so much for watching this webinar. And I think we should just dive right in. There are many questions that have come. Thank you so much for submitting those, and keep them coming. First question I have here is a very cool parametric study. Are there any limitations on the size of the room or the study type? Can I vary other things than the loudspeaker placement? Maybe Daniel, you can take this one since you had that.
Thank you, and thanks for the kind words. I mean, it's important to stress that this can be done at basically any scale. So the room here was around 112 cubic meters, and you can easily go to 500, 1,000, or even larger in the SDK. And we just choose the example here for varying the loudspeakers, but you could as well vary the material properties, for example, of an acoustic absorber and see how that affects the room acoustics.
Awesome. Next question. In the machine learning studies, you always showed plots of the sources and receivers in the room. Do I understand it is right that the information is directly linked to the simulations and can be accessed in the same place as the simulation results? What do you say, Georg?
Yes, that's correct. So we have all of that information in the simulation definition object, how we call it. So we have both the source and receiver configurations, we have the materials all in there, and of course the simulation results. In there you can also access very easily, for example, reverberation time or other acoustic parameters, the energy decay curve. Everything is in one central place, easy to access and linked to the simulation.
Okay, very good. Next question. I want to try the SDK and try running these demos myself. How do I go about doing that? Well, first of all, everyone who signed up for today's webinar, close to 1,000 people, will get the code, all the code that we showed here today, sent via email on Tuesday next week. So if you're a customer, by Tuesday, all these updates will have been rolled out and you get the code and you can just start messing around with it. If you're not a customer yet, then you can apply for a free trial. If you go to our website, it's literally kind of the first big button you see, try Treble for free or something like that, and you fill out the form and then you get access so you can mess around with the SDK and from Tuesday with the notebooks from today as well. Next question. How does furniture in the model affect the automatic grid generation of sources and receivers? What do you say, Georg?
Yeah, this is actually a really good question because usually you really want to make sure that you do not place any sources or receivers right into your furniture, for example. And the good thing in our functionality, both for the generate valid points, but also for the grids and also for the furniture, it has some option in there to specify how far away do you want to be from any surface in the room. And that also includes all of the furniture, of course. So by having that large enough, you can make sure that you will not place any points where the furniture is located. And you could also see that in the simulation definition plots in the presentation. So,
great. Next question. Can I apply changes to the geometry with the SDK or only change the parameters of the simulation, like absorption and source position and so on? Maybe that also goes to you, Georg?
Yes. So a small part of that, of course, I already showed. So we showed that we can place the furniture in there and just kind of put it to different locations in the room and move that one around, rotate it around. That is very easy to do programmatically. If you want to change, for example, the rooms itself, if you think of that example of the polygon room, for example, you will have to create a new room object from that one, but it's still possible to change, for example, some point of that floor plan as we saw in the example.
Okay. Next question or maybe a comment. Hi, I'm interested in creating a simulation using an HRTF and a reverberant room for research purposes. I would say this is exactly what we did in the sort of first demo, showing how you can both simulate the room very precisely and then incorporate some kind of mannequin head device on the receiver end and do this with extremely high precision, both the room simulation, like I say, but also the device rendering. You can go to very high order ambisonics, which is needed if you want to get physically accurate results all the way up to 12 kilohertz and even beyond. So I hope that made sense. More questions. Hello, is there a planned SDK for Unreal Engine 5? What do you say, Daniel, product manager?
It's something that we think is really exciting, the real-time audio applications and these kind of things, and it's something that we are thinking about, but it's also not an area we have entered completely, but it's definitely sort of something we are considering. As a side comment, I can say it should be possible to export scenes and geometries from Unreal in a certain way and then import it into Treble and do your audio renders there. So that could be a good place for you to start if you want to explore this with the Treble SDK.
Nice. Are there any academic license access options for the SDK for researchers? Absolutely. We offer special price and special license for researchers, academic researchers, so just reach out to learn more. Here's a question: do you take care of standing waves and physical vibrations from the outside, like machine rumble, train passing, etc.? So I would say yes and no. Yes to the standing waves. So certainly kind of modal behaviors in rooms and so on is very well captured in the wave simulation. But transmission from outside and in is something that we do not support yet, at least. But that sort of, I would say, is on our roadmap. Okay, how can acoustic properties be assigned to the geometry? Is it possible to use custom absorption parameters? If yes, then how? Maybe this is a bit related to the studio demo.
Yes, so you can, as we showed, design these porous absorbers with defining this flow resistivity and porous layer thickness and so on. But we also have this very nice material fitting feature where you can specify absorption coefficients, reflection coefficients in octave bands or third octave bands, and then import that into Treble, and we will take care of the fitting for you. You can add that to your material library, and you and everyone in your organization can then use that material going forward.
Boom, boom. Let's see. Another question on sound transmission. I guess that's been covered. Another question from a PhD student about the academic license. Also covered. I have to admit that there's a question here that I don't fully understand. How can T20 and T30 be recalculated into reverberation time with decay by 60 dB if the simulated values don't meet T30 times 2? So you'll have to allow me to get back on this one. Let's go to the next one. Apart from standing waves, which was addressed earlier, I would also like to ask about the comb filter effect. And says great webinar also. Thank you for that. Absolutely, comb filtering is captured very well in Treble simulations, both in the web application and in the SDK. The wave solver inherently captures phase behavior and therefore kind of constructive interference and destructive interference, but also actually our geometrical acoustic solver because it's pressure-based or phase-based. Okay, maybe Georg will get into this. This is a question for you, Georg. But do you have results showing the differences in machine learning performance when you train with geometrical acoustics only, hybrid, or wave only Treble data? That's a good question.
Yeah, that's indeed a very good question. So we have results on that. We are actually running quite an extensive study on exactly that question. And the results that we got so far, they really look like the Treble simulations give some benefit in performance to the models that we investigated so far. We still want to write a nice study about this, get this peer reviewed, and have everything like very comprehensive. So there will still, you will still have to give us a bit of time until that comes out, but we are definitely looking into this, and we see some promising results. Yes.
Great. What's the pricing after the free trial is over? I think maybe I came into that in the presentation after this was asked, so I hope it's somewhat clear. Just reach out for a specific quote. Valdemar says, very interesting webinar. Thank you, Valdemar. How does the membrane resolution input on the loudspeaker from the control room study impact the results of the simulation? Daniel, what do you say?
Yeah, I can take that. So you do specify this membrane resolution, this boundary velocity feature, and specifying a true coarse resolution will sort of make your membrane not circular anymore, and that if that becomes too coarse at some point, this will affect your results. What we also showed is that you can go in and inspect the loudspeaker before you perform the free field simulation. So we definitely recommend that after you've chosen this membrane resolution, you go in, zoom into the plot and see, okay, is this the approximate shape of my membrane actually looking good? And I can say we get quite close to these sort of circular shapes. Yeah.
Fantastic. Follow-up question, optimal loudspeaker placement in any room would benefit many industry applications using the Treble web app. Do you plan to add such a feature to the web app? Good question. I would at least say for the time being, the SDK is the tool for doing this kind of optimization tasks and parametric analysis, and it's really kind of well suited for that kind of work, I would say, in automated ways and so on. So I think I would certainly recommend at least the SDK for such a solution at the moment. Who knows what the future may bring, but yeah, hope that's clear. Okay, more questions. Is it possible to make the graphical and audio output available to an XR visor for virtual reality, for example, the MetaQuest? Maybe I can take that, guys. I would say yes. We don't, like was touched upon earlier, we don't sort of integrate directly into like gaming engines or things like that yet for these kind of real-time things. But you can, of course, export the spatial impulse responses that come out of the simulation and then use that for rendering purposes onto, for example, a MetaQuest device. And then you could set up a grid of responses and interpolate between or something like that. So that's something that you could do now to kind of pre-bake results with the Treble SDK and then use them downstream in some real-time application. Would you speak to how Treble would compete or compare with Dolby Atmos? Shall I? Or if you have thoughts? Yeah. I have to admit, I'm not actually an expert in Dolby Atmos, but to my understanding, that's more kind of a format for playing back spatial audio over a loudspeaker system. Treble is more about the simulation of the room and kind of generating these spatial impulse responses. You could, of course, render that to a loudspeaker array and have it being played back, and use it for all kinds of spatial audio work. So yeah, it's a bit kind of apples and oranges, I would say. But yeah, hope it makes sense. And here's actually our last question, which is actually perfect timing because we were going to stop in 1 minute anyway. Is it possible to export high-order ambisonic tracks from the simulation? Daniel, maybe you can?
Yeah, I mean, we support up to ambisonic order 32. And we, of course, encourage our users to work in the Treble SDK with the result object and the functionalities that enables, but you are definitely also more than welcome to download the spatial impulse responses to your device, local machine, and work with those.
Mm-hmm. Okay, came in a good question here in the end, so let me add that one just here. Very compelling solutions. What talents do you anticipate adding to the team to grow capabilities within the different verticals we are targeting? That's a good question. We are at least lucky to have a very talented team here at Treble. I mean, look at these two guys and the rest of the people out here. So we have, expertise across acoustic simulations, audio machine learning, geometry processing, back-end cloud, user interfaces, and then all the commercial side as well. So we're more than 40 people now. So I think we're pretty capable actually for the time being to kind of take on these different use cases and so on. But we, of course, strive to have an even bigger impact with more great talent moving forward. Okay. Thanks so much for watching. Reach out to us if you have any questions, if you want to try, or and just have a great day, night, depending on where you are in the world. Bye-bye.